So, talking about the Friis equation. The Friis equation works very well when the distance r squared is much larger than the size of the antennas of the transmitter or of the receiver. And in fact, this is what we usually do. We try to use wireless communication when we want small antennas and long range. This is the usual thing. But on the other hand, we have a problem. We have a problem when this range is very small. When this range goes to 0, this is our problem. Why is it a problem? It's a problem because if the range goes to 0, this goes to infinity, this goes to infinity, this goes to infinity, this goes to infinity. All the equation in its many different forms, it gives us an infinite result. Or it's not necessarily really that this is infinite. It's enough that we calculate here more power in the receiver than we had in the transmitter. This is something very, very wrong. This is really wrong. How to explain this effect? I will try to make some drawings here. Okay. The first very simple solution is we have a transmitter that is transmitting such a conical beam of radiation. And now we put a receiver that's much larger. This is the surface of the receiver. And this is actually what the transmitter illuminated. Yes, if the range here is too small, this only happens on small ranges. If the range here, the distance between the transmitter and the receiver is small, then we have this problem. So non-uniform or under. So not the whole receiver is illuminated because the beam of the transmitter is so narrow. This can happen. In optics, it's very easy to do this. It's very easy to point the laser just to a single point of a photovoltaic panel. The photovoltaic panel is much larger, but with the laser we illuminate just one single point. So that's the typical thing that happen. So this is for non-coherent receiver. The problem becomes even more difficult if we have a coherent receiver. So for the coherent case, I will draw my transmitter just as a dot here. This is my transmitter. And transmitter is reading here wave fronts, okay? And on a certain distance r, I have a receiver. I will draw just the side view, so I have only one dimension here. This is the receiver that has an area of the receiver. And has also a certain dimension. So this is the dimension of the receiver. So the area will be probably d squared here if it's a square receiver. What happens now? Now the problem if this is a coherent receiver. This coherent receiver is sensitive to the phase of the impinging radiation. So here we actually get spherical waves to the receiver. Now, the problem is that if this goes here exactly touches the surface of the receiver, this wavefront as transmitted by my transmitter. This path here actually is r up to here, and it's some delta up here. I have a phase error here. A phase error. And this difference in the path traveled by the waves results in a path difference. Path difference provides a phase error. So this delta R here actually contributes to a phase error, delta phi. This phase error is comparable to what? Wave number times delta R. Without the dot. I prefer not to write dots because there is not dot provoking. We make a phase error over there because the wave fronts are spherical while our antenna array is flat. If I move the transmitter far away here from my receiver, then these wave fronts at long distance become practically flat and this phase error vanishes. Of course, this phase error is a function of R here. What is the maximum phase error in this case? I will try to calculate this. So maybe this picture is not very good. This should be the center. I wanted to draw the center, but now I see. So this is d half, and this is d half. So according to the Pythagora, R plus delta R is the hypotenusis. So R plus delta R is equal to square root of this one down here is R squared plus d half squared. Also squared. If I square this thing, so to get the equation, so it's R squared plus twice R delta R plus delta R squared is equal to R squared plus d half squared. To solve the equation, and now this R squared cancels out perfectly on both sides of the equation. This delta R squared is very small because the error is small, and I can neglect this one. So I can say that approximately twice R delta R is approximately d half squared. So this is d squared over 4. Or if I try to compute delta R, is now approximately, I should take the approximate sign, so d squared over 8 R. So we have this error quantified here. Now if I can calculate this error approximately, k is 2p over lambda times the wave number times delta R, I have it down here, times d squared over 8r. So this is now becomes 4 lambda. Yes? R2R, cred delta R. Tukaj, če ga imamo, tukaj smo prav, potem ga pa damo sem dol, tale R, damo sem, ta člen prepisujem. Ga damo sem. The two cancels out, p times d squared. And now you see that this error is, at least in our approximation, is proportional to the square of the transversal distance.
Is there still an R?
R, yes. R lambda R. So this phase error is proportional to the square of the transmitted distance. That's the reason why this kind of error is called square phase error. A square phase error always indicates a spherical wavefront. A linear phase error means that the wave is actually traveling in another direction. So if it were the error was proportional to the linear, d squared is square phase error. That's the reason why we call it square phase error. Now we have to see what contribution do we get out of this square error. So let's say the other way around. Let's rewrite the equation now the other way around. So let's find the distance out of the phase error. The distance if we find out of the phase error. So here is still P, is still D squared, is still 4. And we have lambda here. And we have here delta phi. Correct? Delta phi if you put down. So at what distance this thing happens? And what is the contribution of this phase error? And so this is unrelated to the top picture. This with coherent receiver happens before this one. So this is the worst case, and that's the reason why I'm going to make a small table to see various possibilities. What is the size of delta phi? What is the size of the phase error? And I will start with P, then P half, P fourth, P 8. So for 4 different phase error, what is the contribution to the actual gain I get out of this antenna, because I'm going to measure gain or directivity of this antenna. What is the change in gain? We are going to see this later on, how to get this result. And I'm just going to write the result this hour because I don't have the time to do anything else. Here I get around -4 dB. The exact value is 3.9 and something. Here I get around -1 dB. I get around -1/4 of dB. Here again I get -1.06 dB. At what range this happens? So here I put P for the delta phi for the phase. If I put phi, I get d squared over 4 lambda. Here I get P half if d squared over 2 lambda, d squared over lambda, and here I have 2d squared over lambda. At what distance this happens? So if the distance is larger than this, then the gain error is smaller than this figure here. So if I say I take the last figure, 2d squared over lambda, this 2d squared over lambda, this figure is 0.06 dB, so it's very small error. So this distance we have here for a given delta phi, so this error is given, is also called the Rayleigh distance. From 1891. Of course, in optics, not in radio, because radio didn't have directional antennas at that time. But I just want to point out that these things are not that new. How are we going to use Rayleigh distance in practice? Let's get back to optics and see what's the So it's the standard problem, taking your girlfriends to the mountains and taking a picture of your girlfriend. So what's the issue right now? You are in the mountains. Here you have your girlfriend. And here you have your camera. This has a CCD sensor here and has a lens here. A lens with an aperture D. That's what we are talking about. Now, what where is now the problem? Where is the mountain? We have to focus our camera. And our camera, of course, the mountain has to be sharp on the picture. But to be sharp, we have to focus the camera to infinity to get the mountain sharp. But then we have to focus the camera onto the girlfriend that has R. And both the girlfriend and the flower she picked up should be sharp, as well as the mountain behind should also be sharp. What is now R? For the aperture of our lens our camera has. Let's take that our lens has a diameter of 1 centimeter. This is quite a large lens, quite an expensive lens for our camera. What is the wavelength? Visible, so 0.5 micrometers. This is the length. In optics, we are not particularly tricky about, we can tolerate minus 4 dB of gain. So this is okay for optics. This is okay. So let's try to calculate what is R. D squared is, this is 0.01 meter. This is 0.5 times 10 to the minus 6 meter. So the R in this case, in optics, for this data here, is 10 to the minus 4 here, divided by 10 to the minus 6 is 100. 100 divided by 2 is 50 meters. So if you tell your girlfriend to go 50 meters away from your camera so that she and the mountain, they will both be sharp on the picture, the girlfriend will not be very happy because she's going to be very small on your picture at 50 meters distance. That's a problem. You do not have the depth of field you would like to have. You cannot have both the girlfriend sharp and the mountain sharp because you should send the girl 50 meters away. What is the trick? The trick is to reduce the aperture of your camera. Here the aperture was 1 centimeter. To close your aperture down to D is 1 millimeter, or 10 to the minus 3 meter. Now it's 10 to the minus 6 D squared, the Rayleigh distance, divided by 10 to the minus 6 cancels out. And then is 1/2 multiplied by 4 is 2, 1 over 2. So here the distance is 1/2 meter. This is okay. If you put your girlfriend 1/2 meter from in front of your camera and you have the mountain in the infinity, they both are going to be sharp, sharp provided that you reduce the size of your lens by obscuring part of the lens by setting the aperture of your camera smaller than what was required. And this is the function of the camera. So with the aperture of your lens, you actually defined the depth of field of your camera. In radio, we are more demanding. With the Rayleigh distance, we take a sharper criterion because our whole measurement should be, say, 0.1 dB accuracy. Radio. We're measuring 0.1 dB accuracy. We are even 8 times more than the case in optics. So in radio, we are usually using this R much smaller, much larger R. We need much larger R to have some sensible accuracy of our measurements. What does it really mean, this in radio? If we are measuring our antenna at a distance that is too small, we should correct the focus of our antenna. We cannot do that. We are trying to measure the antenna in the same conditions it's going to work in a real radio communication, so at very long distances. At short distances, your antenna may no longer be focused. We may need to refocus our antenna if our antenna is too large. The same happens in optics, but in optics, we have this capability of reducing the aperture of the camera. Many cameras do this automatically right now. There is no longer no manual adjustment of the aperture. And of course, if I reduce the aperture, I reduce the amount of light I get to the CCD. So maybe I will have to increase the time. So you should say to your girlfriend, stay still, because if you move, the image is going to be blurred. What is this size in the case of the antennas we have in our lab? In our lab, at the practical experiments, you have horns that operate at a wavelength of 3 centimeters on many. Because 3 centimeters is a practical wavelength so that you can do many experiments in the lab. And you can still fit inside the lab. You don't need much room. And these antennas have a diameter here, D, of 11 centimeters. What is now the Rayleigh distance? The Rayleigh distance is now 2d squared over lambda, so is twice 11 centimeters is 121 centimeters squared, divided by 3 centimeters is around, this is approximately 81 centimeters. So such an antenna will have its far field. Let's draw now the limit. This is our R, our Rayleigh distance. R, Rayleigh distance, so this is Rayleigh. And with the demanding conditions for radio antennas. So we are using this very strict requirement for the phase error. Here we have the far field. Only here the far field begins. Or also the Fraunhofer region. Here we still have the near field. But this near field is already radiated. We had the reactive field much closer to antenna. And this near field radiated is also called the Fresnel region. The Fresnel region. So about different names, how are these things called? This is also called geometrical optics. And this is wave optics. So just to tell you how these things are called in different ranges of physics. So if we have our transmitting device, we should actually notice that we have now 3 regions, if this is our transmitter. Very close to transmitter, we have the reactive near field. The reactive near field, so this here, the limit is lambda over 2 pi. And then at a much larger distance, we have the Rayleigh limit, where we have the far field here. In the region in between is Fresnel or radiated, near field radiated near field. So any antenna may have all these 3 fields, though for very small antennas compared to wavelength, this thing vanishes. And this far field is given by the Rayleigh distance, by the dimension of these antennas, the dimension. It makes the same if it's transmitting from the receiving antenna, because things are reciprocal. And this is the Rayleigh distance. Here R is equal, here R was lambda over 2 pi from the reactive field, and the large distance is R is now 2d squared over lambda. So that we have all fields defined for the antennas. There is yet another trick, understanding where the far field starts. The question is now what we do when we have a very long antenna. Where do we take D for such a long, very long antenna? If I am observing this antenna from the front, if my wave is coming from the front, then D is always the transversal distance. D is here. To calculate the... So if I observe the main beam of this antenna, it's sufficient to have this short D, the cross sections in the transversal direction. But if I look at the side beams of this antenna, so from here, if radiation is getting from this and from the side, then I have to use D, the whole length of the antenna. Then D is here. So D should be always at right angle to the arrival of the waves to the antenna. So to know which dimension, this dimension should be always at square angle to the direction of the arrival of the radiation or departure of the radiation from the antenna. Now, this picture here, D may be a function of the direction. Especially for very, very long antennas. Some antennas may be very long. Depending what I'm measuring, it is not always practical to, say, have this distance. If I made here an example, say, the same wavelength, this is almost satellite TV. For a satellite TV, there's 1 meter diameter. This is 100 times more. It's 81 meters, not 21 centimeters. And 81 meters will not fit in any laboratory I know. This is way too large. So this Rayleigh distance may Rayleigh distance may quickly become something that will not fit in your laboratory. And also with such a long antenna, you may get into this trouble. But this is only for the lobes of the radiation pattern in this direction. For what is the antenna radiating in front, the end fire radiation of this antenna, this has only this short transversal distance D. Now we have to solve yet the final problem today. I know I'm late. If we are measuring these antennas, I have 2 of them, so antennas are always measured in a radio link. This is the other antenna, okay? Now, the question is, where should I measure the distance R? So, is R this dimension, or is R this dimension? Say R1 or R2. Which one is correct? If the distance is larger than 1, R is practically equal to R2. Say if the distance, the R is much larger than this D here, then it almost doesn't matter whether I take the beginning or the end of the antenna. But if I measure antennas in the lab, then even with the Rayleigh requirement itself for the distance between two antennas is not enough. I still need to know more exactly from where to measure the distance. And now, and we need, for the laboratory experiments, we yet need this final definition. It's the last one for today, but I know it's lots of definitions today. But else we cannot start the laboratory experiments next week, so I have to do this. Absolutely, it must be done this in the lectures. Because without this, we cannot start the laboratory experiments. So I have an antenna. And now this antenna is radiating radio waves. I'm not making nice drawings today. What I'm trying to do, I'm trying to find where do these waves come from. So I will draw lines perpendicular to the wave fronts here. And here, and these lines hopefully intersect, all these lines intersect at a single point. This point of intercept of all these lines that I drew perpendicular to the wave fronts, if they intersect at a single point, this point here is called the phase center of the antenna. If the antenna has one such point. Of course, I can only draw these lines inside the main beam of the antenna. When you go to side lobes of the antenna, usually the phase flips by 180 degrees. So it does not make sense to go to side lobes. In the main lobe, an antenna may have a phase center. So here I should really find out, before doing any measurement, I should find out where is this phase center of the antenna A and where is this phase center of the antenna B, and measure the distance between these two phase centers. This is the correct distance to be done. This is the correct R, the correct distance to make my measurement. So measuring the distance between the antenna, not between the beginning or between the end, but between its phase centers. Now with some antennas, it's easy to guess the position of the phase center out of the geometrical construction of the antenna. With other antennas, the phase center is not that trivial. What do I actually do then? I put my antenna on one position, so a motor that is going to turn everything around. I put my antenna under test here. And I connect the transmitter here. And with the receiving antenna, I measure now the phase between these two antennas. And I also take a sample here of the signal. I measure the phase difference. And if I'm turning my antenna, if the axis of rotation of my antenna goes through the phase center of this antenna, then I have here this angle phi is constant. If the axis goes through the phase center. If I miss the phase center, then the angle here changes. The phase angle changes as I rotate the antenna, because then I'm not turning the antenna around its phase center, so the phase will be changing. So this is the way to measure the phase center, to identify the phase center of an antenna you don't know. Usually, horn antennas have their phase center close to their throat of the horn. So if you have a horn antenna like this, usually the phase center will be somewhere here, close to the throat. Of course, you cannot do all measurements on just one experiment in the lab. So if you have unknown antennas, you should ask the assistant that he explains you where a certain antenna has its phase center, so that you can make your measurements correctly. If you miss this, you may have very large errors, because R1 and R2 are very, very different here. So they will behave very, very different. The result of your measurement, say gain measurement, will be very different if you use R1 on R2. The correct number is R, from one phase center to the other phase center of the antenna. So I hope that's all for today. We don't have, if we have 5 minutes yet for an example just of all this. An example maybe to fit in this figure. Here is just an example for the last thing of today. We have everything now. We have everything we need for the laboratory experiments. We need just an example. And say something you probably missed in the course with optics, and you missed with the laser beam. So we start with the helium-neon laser. That's a typical thing you have with the optics experiments. And this laser generates a beam that's almost parallel at the beginning. The beam diameter here is about 1 millimeter. But after a certain distance, the beam starts diverging into a conical pattern. So now the question is, what is the area we cover here at a distance r is 1 kilometer? Here, what is the area from the laser? So the laser has a wavelength lambda of 0.63 micrometers. With these numbers, I can calculate the directivity of this laser. The directivity is 4 pi over lambda squared times area of the beam. So this is 4 pi. Lambda squared is 0.63 times 10 to the minus 6 meters squared times area. Area is, if this is the diameter 1, this is p diameter square half squared. Okay? So what are the numbers here? What is the directivity of a HeNe-laser? Just to use the equations we had today, just to make a practical example. This is 4 pi squared. In the bottom, 0.63 squared is about 0.4. 0.4 times 10 to the minus 12 meters squared. Here d half is half a millimeter. Half a millimeter is 0.25 times 10 to the minus 6 meter squared. Half a millimeter squared is 0.25 times. So now some things do cancel out here. 4 and 0.25 cancel out. I have 10 to the minus 6, 10 to the minus 12. I have 10 to the 12th power, p squared, and approximately 0.4 down here. 0.4 down here. Meters cancels out. Of course, directivity has no measurement unit. Not 12, 6. If I have minus 6, minus 12 is 10 to the 6. Pi squared is about 10. 10 divided by 0.4 is 25. 25 times 10 to the 6th power. Or in decibels, this is 25 is around 14 decibels plus 60 decibels here. This is around 74 dBi, just to talk about the helium neon laser. Now, what is the area covered here? Okay, we can calculate the omega here. We said that directivity is 4 pi divided by omega. So omega is 4 pi divided by the directivity. And the area the beam is going to cover is omega times r squared. So the area is actually omega is here, so 4p divided by 25 times 10 to the 6th power. This is gain, directivity, times r squared is 10 to the 6th powers of meter squared, if this was 1 kilometer. So the area is 4 pi divided by 25, that's about 1/2. That's about 1/2 of meter squared. So at 1 kilometer distance, this is half a square meter. The beam becomes very broad at large distance. Where is the throat of this beam? Where a parallel beam transforms into a conical beam. This distance here is actually the Rayleigh distance. The Rayleigh distance. We can calculate this Rayleigh distance. This is 2d squared over lambda, where d squared is 1 millimeter. So 1 millimeter squared over 1 meter half squared over lambda. Lambda is 0.63 times 10 to the minus 6 meter. Okay, so we have on top we have 1 millimeter is 10 to the minus 3 meters, squared is 10 to the minus 6, 10 to the minus 6 and 10 to the minus 6 cancels out. It's 0.63 in the denominator. It's on top is twice 2 divided by 4 is 0.505. What is this? Meters. Unit is meters here. So this is something around 0.8 meters. So already at 0.8 meters, our beam starts diverging from a parallel beam into a conical beam. Starts opening. Our beam starts opening. So actually have here, up to here we have Fresnel, and here we have Fraunhofer. So just to explain all these things on an example you can see in the lab, like the helium neon laser. You know that the helium neon laser, if you observe it at a few centimeters distances or even a few 10-centimeter distances, the beam looks like parallel. Up to here looks like parallel. But here at 0.1 meters, the beam starts opening. And it will become much, much larger, let's say, at 1 kilometer distance. First, this opening is very slow because we used this relation for a very strict relation for the Rayleigh distance. This is all for today. Sorry, 15 minutes late. But trying to tell everything. I didn't do this last year. But it's something I have to explain because in English we have very exact expressions for the types of fields we are dealing with antennas. So it's something it was not necessary before to do, but this year it's necessary. Actually, two here, and the final result is not 0.8 meters. The final result is around 3 meters. Sorry for the mistake.